Hey there, computer science students and fellow coding enthusiasts. Welcome to this explainer. Today, we're going to demystify the absolute fundamentals of computer memory management. Look, if you've ever stared at a screen full of code and wondered how, under the hood, all those bits and bytes are actually kept in order, well, you are definitely in the right place. We're going to break down the invisible architecture that literally makes software scalable, fast, and, elegant.
I want to kick things off by having you ask yourself a super direct question. Ready? Are you organizing your data, or is it organizing you? Seriously, think about it for a second. When we write programs, we're dealing with vast amounts of information, right? And if we don't have a solid game plan for where that data goes and how it relates to everything else, our algorithms get totally bogged down, memory overloads, and boom, our applications crash. This is the core computational puzzle every budding developer has to solve before they can write truly effective code.
Okay, so here's our roadmap for today. We're going to cover the need for organization, linear versus nonlinear data, static and dynamic structures, essential data operations, and finally, balancing time and space. Let's get into it.
Starting right off with Section 1, the need for organization. Basically, why structure matters so much.
To really appreciate a great solution, we kind of need to feel the friction of the problem first. Imagine you're tasked with finding the management hierarchy in a completely flat alphabetical list of employees. Sure, finding someone like Ashish is super easy, but who does he report to? Who exactly is on Ganga's team? You literally have no idea. This format totally fails to show interconnections, which really highlights the absolute pain of disorganized data when you're trying to solve a complex relational problem. As our source material wisely points out, quote, a hierarchical framework is more suitable for this objective, end quote. Because specific problems require specific organizational frameworks. You wouldn't use a hammer to turn a screw, right? This is exactly where data structures officially enter our story. They're basically the heroes that allow our algorithms to do their jobs efficiently, organizing data mathematically and logically so that the relationships actually make sense.
Moving on to Section 2, linear versus nonlinear. It's time to classify our data.
Now that we've felt the pain of flat lists, we need to map out our solutions. This taxonomy chart is basically your cheat sheet for navigating computer memory. As you can see, data structures split into two main branches, linear and nonlinear. Pretty much every single structure you'll ever use in your entire programming career fits somewhere right on this tree.
So let's compare these two main branches. Linear data structures store items sequentially. Think of it kind of like a line of people waiting for coffee. Each element is directly linked to the one right next to it, its adjacent neighbor. On the flip side, we have nonlinear data. This is where data is scattered or stored hierarchically. Instead of a straight line, think of a family tree or a complex city map. It models those multi-layered relationships where one item might connect to several others all at the exact same time.
All right, Section 3, static versus dynamic. We're talking memory allocation now.
So, what happens when you don't actually know how much data you'll be storing? Like, what if your new app suddenly goes viral overnight? Well, static structures, like arrays, give you fixed memory. It's kind of like buying a bookshelf with exactly 5 shelves. If you get a 6th book, you're out of luck. Dynamic structures, however, are like a magic bookshelf that actually grows as you add books to it. They adapt efficiently on the fly to prevent memory waste while the program is actively running. Pretty cool, right?
Which brings us to Section 4, essential data operations. Let's talk about manipulating this data.
Okay, up to this point, our data has just been sitting there. Let's introduce the actionable verbs of our programming narrative, starting with traversing. Traversing is the systematic process of accessing every single element in a data structure, one by one. You'd use this when you need to exhibit all the elements on a screen, or maybe execute a specific task across every single item in a collection. Like applying a 20% discount code to every item sitting in a user's shopping cart.
Next up is searching. This is all about finding specific data from a vast set of items. If you've ever frantically searched a massive social media database to find a specific user profile or some old post, you are relying entirely on how well some programmer out there optimized this exact operation. It is absolutely vital for retrieving elements fast.
Then we have sorting. This is your critical tool for rearranging records or elements into ascending or descending order. Whether you're organizing high scores in a video game or just alphabetizing a contact list on your phone, sorting takes chaotic data and applies sequential logic to the whole shebang.
And to round out your programmer's toolkit, we have a few more essential actions. Inserting allows you to add elements, while deleting removes them, obviously. Merging is incredibly useful when you need to combine records from two completely different files into one single cohesive file. And accessing, well, that's the simple but very necessary ability to retrieve or modify a specific value based purely on its location.
So we've got all these structures and all these operations, but let's just hit pause for a second. How do you actually choose which one to use? This right here is the strategic gap between just knowing basic coding tools and truly mastering advanced algorithm design. Because the choice depends entirely on which operation you're going to need to perform most frequently.
Let's look at Section 5, Balancing Time and Space, the ultimate trade-off. This trade-off, it is the ultimate test of a programmer's ability. As our source explicitly notes, quote, the time-space trade-off refers to the balance between the time complexity and space complexity of an algorithm. Every single choice you make is a compromise. Do you want it lightning fast? Well, that might require massive amounts of memory. Want to save memory? Then your program will probably take longer to execute its tasks. It's a constant balancing act.
To help manage these complexities, we use abstract data types, or ADTs. Think of ADTs as high-level conceptual frameworks. They define what the data structure should do without getting bogged down in how it's actually built under the hood. By utilizing ADTs, like stacks and queues, programmers can use pre-existing, proven solutions to manage data cleanly. It lets you craft really elegant code that separates what a structure does from its actual messy implementation.
Let's quickly lock in everything we've covered today with a quick summary. These are the glossary terms you absolutely must understand to pass this unit and start building scalable apps. So remember, linear is sequential, nonlinear is scattered or hierarchical, static memory is fixed, dynamic memory changes on the fly, and the trade-off is always that delicate balance between processing speed and memory space.
And I'll leave you with this final thought as we wrap up this explainer. The next time you open your IDE to write your very next line of code, what are you going to do? Are you just going to choose the easy, familiar data structure, or will you analyze the problem, weigh the time and space trade-offs, and choose the efficient one? The difference between a good programmer and a great one lies right there in that choice. Keep exploring, keep learning, and start building elegantly.